Hey everyone, and welcome to the Chapter 3 lecture for Chem 101, General Chemistry. This chapter is all about electrons and their uber special place in the atom. So last chapter, Chapter 2, we talked a lot about the subatomic particles, all three of them, protons, neutrons, and electrons, but this chapter really focuses on the third, the electrons. So before we can talk about electrons, we need to talk a little bit about energy. Give you a little introduction into energy. Get my pen going here. All right, so energy is defined as the capacity to do work or transfer heat. And there's several types of energy, but the two we're going to focus on in chemistry are kinetic energy, which is the energy of motion of particles moving. All right, so we see this in the different states of matter. They all involve particles that move. So in a solid, they just wiggle a tiny little bit, but in all the way into a gas where they actually fly around a lot. And then we also have potential energy. Potential energy is stored energy. So the classic example in physics is like a ball at the top of the hill, and the potential energy as it goes, then it converts into kinetic energy as it goes down the hill and it's moving. So it has potential energy at the top of the hill because it has potential to roll down, but it has no potential energy at the bottom of the hill because it can't spontaneously roll up the hill. Okay, so the two types of potential energy, though, that are really important in chemistry are chemical energy. And chemical energy is the energy that's stored in chemical bonds. When you break a chemical bond, it actually releases energy that can be used to do work or create heat in a chemical reaction. And then the other type is electrostatic. Electrostatic energy, which is the energy from the interaction of charged particles. So positive and negative charge, opposite charges attract, and like charges repel. And this was really kind of defined as scientific law by Coulomb. So it's called Coulomb's law. And that opposites attract and like charges repel, and that the bigger the charge is and the closer they are together, the stronger the attractions will be and the stronger the energy of those attractions will be. What did the dog do? Okay. Sorry, there's going to be interruptions. Okay, the law of conservation of energy is very similar to the law of conservation of matter or mass. It is that energy cannot be created or destroyed, just like matter cannot be created or destroyed. This is also known as the first law of thermodynamics. Thermodynamics, or thermo for short. Aha! First law of thermodynamics. Okay, so energy can't be created or destroyed. It can be transferred or converted from one form to another. So my favorite sort of fictional example of this is from the movie Black Panther. If you haven't seen it, you should because it's really good. But the Black Panther character, he's a superhero and he has a superhero, spandex outfit. But his tech team designed one that can absorb kinetic energy and convert it to potential energy. So if he gets kicked really hard in the chest, instead of sort of reacting to that and absorbing that energy in his body, the suit absorbs the energy and stores it so that the next time he kicks or punches someone, that energy is released and he has even more energy like in his punch or kick. So it's totally fictional, but it's actually based on a real physics law. And I oftentimes get really frustrated with science fiction because the science is just too fictional. It's not possible. It violates laws of physics. So I got really excited at this concept of like a scientific, of a suit of whatever, that actually respects the laws of physics. So anyway, the SI unit of energy that we'll be working with is joules, and the one-letter abbreviation is a capital J for that. So one type of energy comes from waves, from the electromagnetic spectrum. Different forms of radiation can provide energy. So this is energy from light or other types of rays, and this is called the electromagnetic spectrum. And this is things like visible light and all the way down to radio waves and microwaves, and all the way up to things like X-rays and gamma rays. Thank you, sweetheart. My daughter just brought me a snack.
You can make your own.
Okay, thanks. I'm going to keep recording my video, though.
Okay.
So these different rays have different amounts of energy that's directly related to the wave function. So waves can either be really short or they can be really long. And the short waves, we say, have a high frequency, and the long waves have a low frequency. And the higher the frequency, the higher the energy of the waves. So these waves are increasing in energy as we go right to left. Okay, so waves, all right, are distinct things from particles. At least that's what classical physics always said. So in the early 1800s, all we had was classical physics. And it distinguished these two things, that there were just clear distinctions between waves and particles. They were different. And light was clearly a wave, and matter, like atoms, were clearly particles. And this was defined and undisputed. All right, so some properties of waves that we should talk about are things like wavelength. Define them. Wavelength, which is represented by the Greek letter lambda, and that is the distance between two waves. So the distance between two crests or two troughs would be the wavelength. All right. The amplitude of the wave is the height of the wave. So from the crest to that baseline. And that's related to intensity. So the more intense the wave is, like the more intense a light is, the higher that amplitude will be. And then there's frequency. And frequency is related to energy. Frequency. All right. And that's represented by a Greek letter nu, which looks kind of like a cursive V. All right. And the frequency is the number of waves that pass a given point per second. So if this wave was moving in this direction, if we said it's moving, and so each time a crest hits this detector screen or this point, that would be a mark. And so the number of times it hits that point per second would be the frequency. So wavelength and frequency are inversely related. Wavelength is inversely related to frequency, meaning the larger the wavelength, the smaller the frequency. The larger the frequency, the smaller the wavelength. In a vacuum, all electromagnetic radiation travels at a speed of 3 times 10 to the 8th meters per second. That is the speed of light. We talk about the speed of light. It is literally a speed of 3 times 10 to the 8th meters per second. And we use a lowercase c as our sort of letter symbol for the speed of light. So the speed of light can be calculated. The speed of light is just the wavelength times the frequency. And as the wavelength goes up, the frequency goes down. That's that inverse relationship between the two. The longer the wavelength, the shorter or smaller the frequency is. So there's some, anatomy of waves for you. Now for some of the behavior of waves versus particles. This is how classical physicists distinguish the two from each other. Waves display a response called refraction when they move from one medium to another. So if you shine a light through air and then it hits water, a different medium, the light bends. Okay? Waves bend when they go to a different medium versus particles which curve. If you threw a stone or a ball through the air and it hit the water, it would curve. It wouldn't bend on a different trajectory, it would just curve, sort of slowed by that thicker medium, right? The other feature of waves is diffraction, and diffraction is the tendency of waves to bend around objects. So if you have something that travels as a wave and it hits a wall with a hole in it, all right, it will come out in these sort of bands. That's diffraction. Versus if you have particles that are traveling and hit a wall with a hole in it, they will come out of that, straight out of that hole in a straight trajectory. All right, and so typically light behaves like this. You have a light and it comes out of a little hole and it kind of, it diffracts, it spreads, and it's not like a single band of light versus like a laser beam, which does shoot straight, okay, because it's made actually of particles. So these are characteristics, refraction and diffraction are characteristics of waves, all right? And we just said light does this. So light does refract and light does this, all right? Light refracts and diffracts like a wave. So that's why classical physicists thought light is a wave, all right? But it does have a couple of odd behaviors that suggested that actually maybe light isn't a wave. And these two phenomenon, there's actually three, but I'm only going to tell you about two of them, are the photoelectric effect and the atomic spectra. If you're really curious, the black body effect is the third one, but it's too much physics for me to get into. It's over my head, so I skipped over that one. But these two are enough. Okay, so the realization that these two phenomena existed and that light as a wave couldn't explain these phenomena marked the shift from classical mechanics, field of physics, to a whole new field of physics in the early 1900s called quantum mechanics. And the father of quantum mechanics was Max Planck. Max Planck, he's a German physicist, all right? And he was the first to suggest that perhaps energy is quantized, which is where we get the term quantum physics. That energy is quantized. That we think of energy as occurring along a continuum, that you can have any energy along this continuum, but maybe energy from atoms can only be emitted at certain energies. So like steps, all right? You can't step at a level between the steps, right? If you're going upstairs, you can only stand on the level of each step. It's not continuous. You're going from one level to another. That perhaps energy is quantized, that it's not continuous, all right? Classical mechanics was this continuous model, and Max Planck suggested maybe we're thinking about this wrong. All right, so let's go through some of those weird things that light does and why they can't be explained by that continuous model of classical physics. The first is that photoelectric effect. So the photoelectric effect is this phenomenon where if you take a piece of metal and you shine a light on it, sometimes you can get electrons to pop off. All right. And it doesn't matter how long you shine the light or how bright the light is. That determines the electrons popping off. It's actually the frequency of the light that determines it. So the first thing about the photoelectric effect is that it depends on a threshold frequency. Threshold frequency. All right. The light must meet the minimum frequency for the electrons to be emitted. So in this case, the frequency is too low. You could shine this light on this metal all day long and you wouldn't pop off a single electron, right? Which is weird. Classical physics, classical mechanics says that the intensity of the light is what's important. So they would say that if you just turned the light up brighter, made it brighter, all right, had more of these, then you would get electrons popping off. But that's not true. It doesn't matter. If it doesn't meet the threshold frequency, doesn't matter how long you shine the light, it's not going to work. So that's weird and inconsistent with what classical mechanics predicted. The other thing is there's the absence of a lag time. Again, classical mechanics would sort of assume that the energy would be absorbed over time by the metal, and when enough energy had been absorbed, then it would start popping off electrons. But that's not what happened. What happens is if you shine a light of the appropriate frequency, immediately you get immediate emission of electrons. And then the more light you shine, the more electrons pop off. But immediately, if it's the right frequency, it pops these electrons off. And if it's an even higher frequency than that, you can get them to pop off even faster. Or they move faster when they pop off. They'll fly off even faster. Right? So this phenomenon was well observed. Lots of people observed this phenomenon, but none of them could explain it using classical physics. Until Max Planck and his friend Albert Einstein got together. Albert Einstein, all right, a few years later, in 1905, after, kind of chit-chatting with Max Planck, and who had this idea that maybe energy is quantized, he extended this to light energy. And he said, well, maybe light energy is quantized, and that light actually acts as a particle sometimes. And he called this light particle, or packet of energy, a photon. Okay? So he hypothesized that one photon, one light packet of energy, provides the energy to emit one electron. And then if you have multiple photons, you can emit multiple electrons. And he had a formula for this energy of the photon. It was Planck's constant that Max Planck came up with, which is this right here, times the frequency of the light. So if the frequency is high enough, then the energy of the photon is high enough to eject an electron. So basically what he realized was that light intensity, the brightness of the light, is actually related to the number of photons, not to the energy of the photons. The energy of the photon is related to the frequency. And that's why the photoelectric effect is what it is, that the frequency determines the energy of the photon. And if the energy of the photon matches the energy of the electron, it'll pop it out of the metal. So basically, his theory and his equation, which does explain the photoelectric effect, requires light to be both a wave and a particle, which was just absurd, really. How classical mechanics says you're one or the other. How can you be both? Okay? Quantum mechanics is super trippy. That's my conclusion about quantum mechanics, is in quantum physics, everything is possible all at once, simultaneously. You can be a wave and you can be a particle. This is called the dual nature of light. And it was really revolutionary and started this whole field of quantum mechanics, because it did explain how the photoelectric effect could be, but also how light can do diffraction and refraction. So that became accepted. So let's do a little math here, a couple of math problems. We have blue light that has a wavelength of 450 nanometers. Determine the energy of the photon energy. All right, so we're going to do little writing down equations first. So we have Einstein's equation. The energy of the photon is equal to Planck's constant times the frequency. All right. But we were not given the frequency. We were given the wavelength. We did have an equation earlier that said that the speed of light is equal to the wavelength times the frequency. All right, so we've got these two equations. What information do we have? Well, h is a constant and c, those are constants that we look up. Planck's constant and the speed of light, all right? And in the problem, we're given the wavelength in nanometers, all right? So what we could do is we could solve for frequency and then plug that frequency in here and then solve for the energy of the photon. Another way you could do this is you could rearrange these equations, sort of merge them together, and you could get this equation. If you do some substitution, you can get this equation. Energy of the photon equals Planck's constant times the speed of light over the wavelength. And then you have these two constants, you plug in the wavelength that you're given and you find the energy of the photon. But I'm going to actually not do that. You can do that. I commend you for doing it if you have the algebra skills to do it that way. But I'm going to do it this way, which is actually the longer way. But so first I'm going to do this equation down here, the speed of light. I am going to rearrange this equation. So I want to solve for frequency. So frequency is, excuse me, equal to the speed of light over wavelength here. So that is 3.00 times 10 to the 8th meters per second divided by 450 nanometers. All right, there's a problem here. I obviously want my units to cancel out, my meter units. Frequency should be in inverse seconds. That's the units of frequency. So, but I have a problem because I have nanometers and meters. So I'm going to convert this nanometers down here into meters. So 1 meter is 10 to the 9th nanometers. So now my nanometers will cancel out and my meters will cancel out and my answer will be in inverse seconds. So I actually have to do this on my calculator because I did it the other way in my notes. But I felt like doing it this way live. So let's do 3 EE 8 divided by 450 times 1 EE 9. And that gives me 6.666 times 10 to the 14th. All right, so that's the wavelength. That's a pretty large wavelength. All right, so now I'm going to use this equation up here to solve my energy of the photon. Oh wait, sorry, that's not a wavelength, that's a frequency. Inverse seconds. All right, so now I'm going to do Planck's constant, 6.626 times 10 to the negative 34th. I don't know why that superscript looks so tiny, but it's 10 to the negative 34th. Joules times seconds, all right, times the frequency, which we just calculated to be 6.666 times 10 to the 14th. Inverse seconds. All right, so our seconds and inverse seconds will cancel out, and we'll end up with joules, which is what we want our units to be since it's energy, and joules is the unit of energy. So times 6.626 EE negative 34. And let's make sure I got the same answer that I got in my notes, and I did, so either way it should work. My answer for the energy of the photon is 4.4, and I'm cutting it off at 2 sig figs because this number is 2 sig figs. 4 and 5 are significant, but that 0 is not. 4.4 times 10 to the negative 19th joules. That's how much energy is in a single photon of blue light. Okay, the next question is sort of a follow-up question. It says how much energy is in a mole of photons of blue light. All right, so if one photon is 4.4 times 10 to the negative 19th joules, all right, and then a mole of photons is 6.022 times 10 to the 23rd of that, right? Another way to maybe write this out so you can see units canceling is that this is how many joules per one photon, all right? And this is how many photons are in 1 mole. So our answer will be in joules per mole. All right, so we do some multiplication, and we get 2.66 times 10 to the 5th times 10 to the 5th joules, or joules per mole. All right, so you might have some problems like that. And I'm thinking of a lab for next week where you're doing a lot of these calculations, actually. So removing electrons from metal, which is what happened in the photoelectric effect, requires energy because of electrostatic attractions. We talked about different types of energy. One type of energy is electrostatic attractions, oppositely charged things being attracted to each other. And in an atom, the electrons and the protons are oppositely charged and attracted to each other. So it does require energy to remove those electrons. They don't want to leave. They're attracted to the protons. Alrighty, so that's the photoelectric effect and how Einstein explained that phenomenon by saying light is not just a wave, it's also a particle. And we call that particle with a discrete amount of energy a photon. But there was another weird thing that didn't fit with classical physics, and that was the atomic spectra. So when you take light and you shine it through a prism, you get these patterns. So if it's white light, like from the sun, and you shine it through a prism, you get a continuous sort of spectrum of color that we call the rainbow, and it's continuous. But if you take an element and you excite it with electricity and make it emit light, all right, and then you shine that light through a prism, you don't get a continuous set of colors. You get discrete bands of color. And that's weird. Again, classical physics says things are on a continuum, that energy is on a continuum. But this atomic spectra suggests that the light energy coming off from atoms of an element are not continuous. They are quantized. You just get these specific packets, these specific amounts of light energy. And so, again, we've got to have a different explanation for it. So the person who came along and explained why this might be was named Niels Bohr. Excuse me. And Niels Bohr, in 1913-ish, proposed his model of the atom, the Bohr model of the atom. And so he was building on Rutherford's model of an atom. So remember, Rutherford was the one who did the gold foil experiments and realized that there's a dense mass at the center of the atom, the nucleus, and that the electrons are in an empty space, largely empty space around that. So there's a few electrons floating around in this cloud outside of the nucleus. But he did not propose any sort of organization of those electrons. He just thought they were just kind of like floating around. And he had no idea. But what Bohr suggested was that the electrons actually orbit the nucleus in discrete circular energy levels. So in these different orbits. So like what Bohr thought, so this would be Rutherford after his gold foil experiments. But Bohr proposed something more like this, which is what we still teach today to like elementary school students and stuff. Okay, that electrons are in these orbits like planets around the sun, and that each of those orbits is an energy level. And the ones that are closer to the nucleus are lower energy, and the further away from the nucleus are higher energy levels. And we number these energy levels, and we call the energy level for short, we call it N. So you can have an N of 1, or an N of 2, or an N of 3, and so on and so forth. We say that he said that each level contained a certain energy. So in other words, he said that the energies were quantized. That electrons couldn't exist between levels. They could only be in a discrete level. Okay? So those levels are quantized. He said the lower energy levels are closer to the nucleus. And so the lowest energy level, an N equal to 1, is, we would call that the ground state. The ground state level, the lowest level. And then the higher levels are the excited states. All right, and he said that electrons can jump from the ground state to an excited state, and then they can also fall back down from an excited state to the ground state. So these are called quantum leaps. Quantum because they are quantized, they're discrete amounts of energy, and leaps because they're moving from level to level. So if the electron absorbed energy, if you get absorption of energy by an electron, like from a photon of light, then it can cause the electron to get excited and jump to a higher energy level. All right. So the electron is not terribly stable though at that higher energy level. So eventually it'll fall back down. And when it does that, it'll emit energy. So emission is when an electron emits energy in the form of a photon when it falls back down from an excited state. Okay. So essentially he said you could get electrons by shining light on the element, on the atoms. You could excite the electrons to different energy levels, and then those excited electrons eventually fall back down, and when they do that, they emit light of a specific wavelength based on the quantized energy of that leap. And he showed that for hydrogen, if he did that, if he shined light on hydrogen and then let the electrons fall, and if he shined light on hydrogen and he split up the light, you'd get this spectrum that corresponded to these electron quantum leaps that he calculated for hydrogen. So his model perfectly explained the atomic spectra of hydrogen. And that was great. It was a really great model. But it kind of fell apart when we got to the other elements. So larger elements, so hydrogen only has one electron. So this model worked really well for one electron. But atoms with multiple electrons have all these confounding variables, namely repulsion forces between electrons that make it not work out so perfectly. But it was a really good model, and it's one we still use for teaching today, but has been built upon in recent years and expanded to be a little bit better and be consistent with all the different atoms, not just atoms of hydrogen. All right. So the first person who sort of tried to explain why Bohr's model doesn't work for other atoms was de Broglie in 1920. And he basically said, well, light can act as a particle and a wave, so why can't electrons? So he was the first to propose that electrons are both particles and waves. Just like light, we have a dual nature of light. Well, guess what? There's a dual nature of matter too. It's all very trippy in the field of quantum physics. So this explanation would explain Bohr's quantum or quantized energy levels. Because if electrons act as a wave, all right, a wave, an orbit that's made by a wave has to be in whole number, integer. So the waves have to be able to be continuous around this circle. All right. If the wave is a fraction, or the wave doesn't, fit around that circle properly, it's not continuous around the circle and overlaps funky, then that level can't exist. So he was saying that the energy levels exist, and these quantized energy levels existing could be explained if we think of electrons acting as waves rather than particles. So that was one thing that happened. Then another experiment was this famous experiment called the double slit experiment that was also trying to look and see, do electrons behave as particles or do they behave as waves? So remember we said that if we, if something that acts as a wave hits like a wall with a hole in it, it will diffract. And if there's two holes in it, then it will diffract and these diffraction patterns will overlap. And ultimately when they hit a screen, a detector screen, they'll form these patterns based on waves sort of adding and canceling each other out. So this is how we expect a wave to behave, and the pattern that we would expect something behaving like a wave to form on the screen. If you shoot particles through a slit, all right, they should go straight through. So if something is behaving like particles and you have two slits, you should just get two lines, all right? So this is the result we expect if something is behaving as a particle, all right? Well, what they did was they took electrons and fired them at this, screen with two slits in it. And what they found, the results were what you would expect for a wave. In other words, these electrons were behaving like waves and not like particles. So this was further evidence that electrons can do both. We already know they have features that are particle-like, but they also have features that are wave-like. So not only is light a wave and a particle, but electrons are also waves and particles. Yay! So these two different features, the wave nature and the particle nature, are what we call complementary properties. Complementary properties. And in physics, complementary properties are ones where if you know, the more you know about one, the less you know about the other. And so the more we know about the wave property of nature, the less we know about its particle properties. It's, again, kind of over my head in the trippy physics area, but the Heisenberg uncertainty principle is one that focuses on these complementary properties. So electrons have both velocity and position. We know that they move around, but that they also have they move around, but they also have this, probability of staying in one spot for more time than others. All right, they occupy these different energy levels, but they're also simultaneously moving. But because velocity and position are complementary properties, the more we know about one, the less we know about the other. So we can't really ever know exactly where an electron is. We can only know where it probably is. We can only express the probability of finding an electron in the electron cloud. And the person who kind of put some math to Heisenberg's principle was Schrodinger. So Schrodinger has some complicated math equations that we won't get into in order to determine where an electron is going to be positioned. So this is a picture here looking at the probability map of an electron. So a given electron in like the first energy level could be anywhere in this zone, and there's some denser places where it's most likely to be. But it could be a little closer to the nucleus, it could be a little further away. So when we are talking about like the size of an atom, atoms don't have like a discrete, exactly defined edge. All right, the electrons are always kind of moving around. They're kind of fuzzy. So the atomic size is really more like a probability contour, a 90% probability contour, where this area where we're 90% confident that the electron can be found in, but it won't 100% be found there. And quantum mechanics and Schrodinger's equations changed the shape of those energy levels from two-dimensional orbits like Bohr had them, and they're actually complex three-dimensional shapes. So energy levels also have sublevels, they realize, and they have these different funky shapes that we'll talk about. So Bohr was right in essence that there are different energy levels, but he was wrong about their shape. Their shape is much more complicated. And so electrons reside in these different energy levels, but the energy levels can be subdivided into further sort of spaces. So we've got an energy level, and you can divide the energy levels up into sublevels. And the sublevels are made up of orbitals. And 2 electrons fit in an orbital, and each electron is spinning in a different direction. So we can also identify its spin. So these are 4 different things that we can determine about, or estimate anyway, the probability of, about the location of an electron in an atom. And we can give them a sort of address based on what energy level, sublevel, orbital, and spin they have. And so I call these addresses, they're called quantum numbers. And there's 4 different quantum numbers. So each electron can have an address, like a 4-number address of those quantum numbers. And I like to call it an address because my analogy here is that the energy level is sort of like the broadest. So you kind of think of the energy level as like the state, if you're talking about your address, what state you live in. And then you start getting more specific. So the sublevel is more like the city or town. And then the orbital is even more specific. So that would be like the street name. And then the spin is super specific. So that would be like your house or apartment number. Okay. So that's my sort of analogy for quantum numbers, that it's really just like an address. And there's 4 different numbers, just like there's sort of 4 different features of an address that go from macro to more micro. So the first quantum number is called the principal quantum number, And we represent it with the letter N. And so we're keeping that from Bohr. Bohr used energy level with an indicator of the level of the letter N. So N represents which energy level. And energy levels, as they go up in size, and they go up in distance from the nucleus. And they go up in energy. Sorry, I'm snacking. All right. So the larger the N is, the further away that energy level is from the nucleus, and the larger that energy level is. The N number, and it can be any integer, by the way. So N can be any integer starting at 1. 1, 2, 3, 4, 5, 6, whatever. And that number also is going to represent how many sublevels, the number of sublevels that the energy level has. So energy level 1 only has 1 sublevel, but energy level 3 has 3 sublevels. All right, so speaking of sublevels, what is the address component that addresses them? Well, that's the magnetic quantum number, and we represent that, that's the angular momentum quantum number, and we represent that with the letter L. And usually it's like a cursive italic L. All right, and the allowed values for L are any integer starting with 0, so it starts with 0, 1, 2, up to anything that is n minus 1. So I'll show you what I mean by that. So an L equals 0. So if you have an energy level, let's say you have an energy level of 2. In the second energy level, that means you can have 2 sublevels, 0 and 1. All right, so 1 is 2 minus 1, n minus 1, so it can go all the way up to 1. If you had an n of 14, I'm not even sure that exists, all right, then you could have 14 sublevels named 0 through 13. Okay, so the sublevel with an L quantum number of 0, we have names for all these sublevels, or letter names. So L of 0, we call that the S sublevel. An L of 1, we call the P sublevel. An L of 2, we call the D sublevel. And an L of 3, we call the F sublevel. And that's just something you have to memorize. S, P, D, F, L, 0, 1, 2, and 3. All right? So energy level 2 has 2 sublevels. It would have S and P as sublevels. But energy level 1 only has 1 sublevel, so it only has the S sublevel. Energy level 4 has 4 sublevels. It would have all 4 of these guys. All right. The third number, quantum number, is called the magnetic quantum number, and it's represented by M sub L. P.S. I don't care if you know these names. I never refer to them by the names. I refer to them by their sort of abbreviation. So that's what you should know. So M sub L can have any value from negative L to positive L. So it depends on what the L value, the sublevel value is. And the number of values of M sub L tells us the number of orbitals in a sublevel, in the sublevel. All right, so L of 0, that's an S sublevel. All right, it can only have 0 as its M sub L. So it only has 1 orbital. So S sublevel has 1 orbital. L of 1 can have M sub L values from negative 1 to positive 1, negative L to positive L. So it has negative 1, 0, and 1. That's 3 different values representing 3 different orbitals in the P sublevel, and they are pictured here. All right, they have a funky dumbbell sort of shape. And they're the same shape, but they're in 3 different planes. So we call them the 3 orbitals, -1, 0, and 1. Those are the addresses, or the m sub l quantum number for each of those 3 orbitals in the p sublevel. If you have an L of 2, that means that your m sub l values can go from -2 to +2. That's a total of 5 orbitals. So the d level, because 2 is the d, an L of 2 is the d sublevel, has 5 orbitals. And then finally, an L of 3, which is the f sublevel, can have a total of 7 different m sub l's, which are the names of the 7 different orbitals in that sublevel. All right, orbitals, by the way, can hold 2 electrons each. All right, so the F sublevel, all right, so F has 7 orbitals times 2 electrons. It can hold a total of 14 electrons. All right, and we'll talk more about that in a minute. The last number, the 4th number, quantum number, is the electron spin number, or the m sub s. And electrons can spin either clockwise or counterclockwise, or sometimes they spin up or down. There's different ways to indicate it. But the quantum number way to indicate it is that they have +1/2 or -1/2. So these are the only 2 allowed values for m sub s. You can't have an m sub s that's like 1 or 5 or 2.5. Those are your only choices. Okay, so this page here is a great reference sheet, your sort of cheat sheet for all of the different quantum numbers and the different allowed values for each. Okay, I am a visual person. I like this flow chart here. So if we have, so we start always with the N, the energy level, all right? And let's pretend we have an N of 2. We're in energy level 2, all right? Remember that 2 also means that there are 2 possible sublevels, all right? So that means that we could have an L of either 0 or 1, and we call those subshells S and P. And the subshell S has only 1 possible m sub l value, meaning it has 1 orbital, whereas the subshell P has 3 possible m sub l values, which means it has 3 orbitals. Those orbitals are represented by these little boxes, right? And notice that these boxes are sort of in line with one another. That's because sublevels contain degenerate orbitals. So degenerate in this context means that they are equal in energy. So each of these 3 p orbitals have the same energy, right? And each orbital, we said, can hold 2 electrons. Okay, so we could have, if you have an atom that has 2, an atom with two energy levels, electrons in 2 energy levels, all right, then they could fill the s orbital. Let's see if I can draw these. Oops, that's a weird pen. Let's go back to this one. All right, so there's my electrons drawn as sort of an up arrow and a down arrow. And they could also be in the p orbitals. Each of those orbitals could hold 2 electrons. All right, and then what we could do is I could say something like, what are the 4 quantum numbers of this electron? All right, quantum numbers refer to a single electron. So for that electron right there that I just circled, all right, its N is 2, because we said that it's energy level 2, and its L is 0. It's in the first sublevel of the S sublevel, and its M sub L The only thing it can be in L of 0 is 0. And its spin, because it's pointing down, I'm going to say it's -0.5. Okay? We could do that for another one too. Let's do it for this one here. All right, the 4 quantum numbers, the address of this electron. Again, we're in energy level 2. Now we're in the p sublevel, which has an L of 1. The p sublevel has 3 m sub L values, but the way that this one is labeled, this one is +1, so we'll say m sub L of 1, and the arrow is spinning up, so I'm going to give the spin number +1/2. Okay, so you could have problems like that, and we'll practice some throughout the lecture. Other types of practice problems we can do. This first one here, indicate the number of subshells, the number of orbitals in each subshell, and the values of L and m sub L for orbitals in the n equals 3 energy level of an atom. So shell and energy level are kind of synonymous. All right, so we have an n of 3, okay? That means that there are 3 subshells. So the possible L values are 0, 1, and 2. Or if we wrote out the letters, S, P, and D. Now it wants to know what, so those are the possible L values that you could have in the 3rd energy level, an N of 3. What are the possible M sub L values? Well, it depends on the L value. So if you have an L of 0, you could have an M sub L of 0. If you have an L of 1, you could have an M sub L of -1, 0, or +1. And if you have an L of 2, you could have an M sub L of -2, -1, 0, +1, or +2. And those are all the possible values. All right. Another type of question that you'll see are ones where it asks you what's wrong with this set of quantum numbers. So it gives you a set of quantum numbers and it says it's erroneous. Why? What's wrong with it? So we're going to go through it step by step. So first, n equals 4. N is it's the 4th energy level. Well, there's nothing wrong with that. N can be any integer, so it can be 4. What it can't be is you can't have n equals 4.5. All right, that would be wrong. And you can't have it be negative either. You can't have n equals -2. All right, those would be incorrect n values, but any positive integer is fine for n. So this one is kosher, it checks out. Now we go over to L. L equals 1. L can equal 1. The question is, can it equal 1 if you have an n of 4? And yes, for an n of 4, L could be 0, 1, 2, or 3. So an L of 1 is kosher. All right, L of 4 would not be, because you could have an L of 4 if n was 5, but not if n is 4. All right, so then we go to the m sub L value, and it depends on the L value. So if L is 1, then our m sub L possibilities are -1, 0, and +1. All right, so -2 is not possible if you have an L of 1. So that is what is the problem with this set of quantum numbers here. All right, it's not that it's negative. M sub L can be negative. All right, it's the only one. Well, no, M sub L and M sub S can both have a negative value. It's that it doesn't fit. It's not possible with an L of 1. All right, and magnetic spin can only be positive or -1/2. So any other number for magnetic spin would be erroneous. All right, so we keep talking about these sublevels as having an L value, but also having a letter value. And we more often, like as we move on in this chapter, we're going to be using that letter value a lot. So we do talk about electrons in sublevels, and we can name those sublevels by combining the N value with the L letter designation. So an electron with an N of 1 and an L of 0 would be, we would say, in a 1s orbital. And an N of 3 and an L of 1, that's a P. So that would be the 3p sublevel, or a 3p orbital. The next one, energy level 5 and an L of 3 is the F sublevel, and energy level 2 and an L of 1 represents the P sublevel. So there might be some problems just practicing that. Okay, so quantum numbers are really good for talking about individual electrons in an atom. But most atoms have multiple electrons, and they have multiple energy levels and orbitals that fill with electrons, but they fill in a very organized way, and there are rules that govern the order of their filling. Drink break. The first rule is called the Aufbau principle. Aufbau principle. And the Aufbau principle just says that electrons are going to fill the lowest energy levels first, and that they can fill with 2 electrons per orbital. So they'll fill 1s first, and then 2s, and then 2p, and then 3s and 3p, and then they fill 4s before they fill 3d, which is a little counterintuitive. You'd think they'd fill all the 3s first, and then the 4s, and then the 5s, but it just happens that these energy levels overlap. So 4s is actually lower in energy than 3d, so it will fill 4s before 3d. All right. The next rule, so when we're trying to fill the p orbitals, which are 3 degenerate orbitals, we follow Hund's rule. And Hund said that electrons will fill degenerate levels singly and with parallel spins first. So something like that. Not like this. All right, with opposite spins, and not like this. They won't fill the first one with 2 and then move on to the second one. They don't fill like that. So those are 2 wrong ways. Hund's rule says they will fill one at a time in the same spin, and then they'll start doubling up. Do, till they're full. I use a swimming pool analogy. So I used to be a swimmer. I go to the swimming pool to swim laps, and if there's nobody there, I get my own lane. Great. And if somebody else comes in, they're going to take their own lane, because we like our personal space. So apparently electrons do too. They want their own lane, their own orbital, before they're willing to share with another electron. But then if there's, a lot of people at the pool, you have to start sharing lanes. And so only then do you share. You don't usually share a lane unless there's no other lanes available for you by yourself. All right. And then the third rule is called Pauli's exclusion principle. And Pauli's exclusion principle, all right, says that no 2 electrons can have the same 4 quantum numbers. In other words, they can't occupy the same orbital with the same spin. So you can have this, 2 electrons in an orbital with opposite spins, but you can't have this, okay? So that is a no-no. You can't have 2 electrons with the same spin, because if you did, they would both have the same 4 quantum numbers. Both of these electrons would have an N of 1, an L of 0, because they're S, an M sub L of 0, and a spin of positive 1/2. All right, so you can't have that. So let's do some example orbital diagrams. Now, before we do these, I just want to say that in the textbook and a lot of worksheets and stuff, orbital diagrams are drawn as boxes. So you would have, like for the second energy level, you'd have something like this. It'd say 2s and 2p, and you draw your electrons in the boxes. I like this sort of dash method because it's cleaner on paper and easier to write, but they're the same thing. All right, all we're doing is we're diagramming out the different orbitals and the different sublevels and the electrons in them. So let's start with nitrogen. If you don't have your periodic table out already, now's the time to get it out. You're going to keep it out for the rest of this lecture because we're going to use it lots and lots. So nitrogen, on the periodic table, you find it. Its atomic number is 7. It has 7 protons, which means it also has 7 electrons. So let's fill following these rules. We've got 1, 2, 3, 4, 5, 6, 7. So we filled the lower energy ones first, and then we moved into the 2p, which has degenerate orbitals. So we put 1 electron in each of them before we would double back. Silicon, using your periodic table, you find silicon, it's got an atomic number of 14. So let's add those 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? And then one more, we'll do potassium. Potassium is in group 1. It's element number 19, 19 protons and 19 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, easy peasy. The hard part is if you have to write out those diagrams, the 1s, 2s, 2p orbitals first. Okay. Little pop quiz question for you here. This orbital diagram is showing all of the electrons in a potassium atom. But remember, quantum numbers are for describing the address of a single electron. So here's an electron that I'm pointing to, and I want to know what are the quantum numbers. What's its address? Well, it's in the second energy level, in the p sublevel. So that means it has an N of 2 and an L of 1. And if we were to label these orbitals with M sub L numbers, they would be -1, 0, and +1. So I'm going to say the M sub L is 0. And the spin is down, so it's a -1/2. Okay? Just reinforcing and practicing those quantum numbers. So back to these orbital diagrams. Orbital diagrams are a great way to visualize all the electrons in an atom, but they can be a little bit tedious. And so there's a shorthand way to write out that electron configuration, and it's called electron configuration. Electron configuration. All right, so if this is the orbital diagram for nitrogen, where we have the orbitals sort of mapped out and we've drawn those electrons and their spins, okay, this is the shorthand for that. So in the 1s orbital, we have 2 electrons, so we put a little 2 as a superscript. 2s, we have 2 electrons, and in the 2p, we have 3 electrons. So the number of electrons in that orbital just becomes the superscript. And we call this the electron configuration. They show the same thing, just in 2 different formats. But make sure you understand the difference, because if a question says draw the orbital diagram, that's a different thing than writing the electron configuration. So you want to make sure that you know which is which. All right. So this question says, draw the orbital diagram and electron configuration for iron. All right, and if we look on our periodic table, there's one if you scroll down at the bottom of this page, and I'm just going to look at it on my screen. So iron is element 26. 26, meaning it has 26 protons and 26 electrons. So I'm going to fill 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and oops, there's 5 d orbitals, so I got to draw a fifth one there. 25, 26. Okay, and if I was going to write this out, so that's the orbital diagram. Check, I did that. Now to write the electron configuration, all right, it's simply 1s2, 2s2, 2p6, 3s2, then 3p6, 4s2, and then 3d has 1, 2, 3, 4, 5, 6 electrons in it. So that would be the electron configuration for iron. So electron configuration, oh man, there we go. Electron configuration is something that we can so we can write it all out. We can write out the electron, the orbital diagram. We can figure out how many electrons an element has using the periodic table, and then write it out that way. But there's actually a quicker way to do it based on the periodic table. And that's because the periodic table is actually arranged in a very specific way. It's got that weird shape, but it has that weird shape because it's actually organized by electron structure. So originally, when people were sort of building this periodic table of elements, Mendeleev, who's really sort of the father, considered the father of the periodic table, he grouped elements in these columns that of elements that had the same properties. All right, they had the same properties. And it turns out they have the same properties because they have the same electron configurations. Turns out these properties are due to electrons. They're kind of like the most important subatomic particle, if you ask me, because so much of chemistry is dependent on electrons. It's not even funny. And the periodic table, basically, is arranged based on similarities between electrons. So let's just look at this group here. This column here, really just we're looking at these three: fluorine, chlorine, and bromine. All right, let's look at their electron configurations. If we wrote them out, fluorine has 9 electrons, so that would be 1s2, 2s2, 2p5. Chlorine has 17, this would be the electron configuration, and bromine has 35. Do the math, this would be the configuration. But look at how they all end. 2p5, 3p5, 4p5. They all have the same ending. They all end in p5. And they're all in the same column of the periodic table. Turns out that all of these guys in this column end in p5. All right? So you can actually use so we don't even have to, like, I could say, what is the ending of iodine? And you would say p5, because everything in this column ends in the same thing. Turns out we can do this with the whole periodic table. We can break it up into these sort of blocks. So the first 2 columns are the S block. So the column 1 ends, everything's going to end in S1. And in column 2, all of the electron configurations end in S2. Skip over to the P block over here. These all end in P1, P2, P3, P4, P5, P6, so on and so forth. All right, and so the reason the S block is 2 columns is because the S sublevel only has 1 orbital and can only hold 2 electrons. The P sublevel, the P block, is 6 columns wide because the P sublevel has 3 orbitals and can hold 6 electrons, and so on and so forth. So there's a reason why these sort of columns are in the numbers and the orders that they are. So some things to know: these S and P blocks here, the elements in those 2 parts of the periodic table are known as main group elements. And they're the ones that, if you move on in chemistry and you go to like organic chemistry, you spend the most time with those. And they are sort of the easiest chemistry-wise. They do behave in very predictable ways. The D block here, we call these the transition elements. And they can do some weirder things that we'll talk about. And then the F block down here, we really won't even be working that much with this semester. That's higher level inorganic chemistry. And these are called the inner transition elements. And I'm not sure any of them occur naturally. Well, a handful of them do. Some of them are man-made. So for the S and P blocks, you'll notice that the energy level matches the period number. These are the period numbers, the row numbers, 1, 2, 3, 4, 5. So this top row is 1s. The second row is 2s and 2p, 3s and 3p. All right, the D block, though, you'll notice is offset by 1 number. So it goes from 4s to 3d. So in the 4th row, the energy level in front of your D is going to be the period number -1. So like in the 4th row, 4 minus 1 is 3. So anything in the 4th row, D level is the 3D level, not the 4D level. And then the same thing for the F block, it's offset by 2. So the F block fits in right here. So 6S then becomes 4F, which then becomes 5D. All right, so we're gonna like read it all off in order here and show you that. So before, in an earlier page, I had that energy diagram that showed you the order of filling, so of the different energy levels. So it looked something like this, and you had the different energy levels and the different orbitals, right? But if you use your periodic table, you don't even need to reference that because the periodic table shows you the filling order. And this is the filling order, and then we're going to follow it across the periodic table. So we start with 1s, and we fill the 1s. Then we fill the 2s. Then we go across and fill 2p, and then we fill 3s, and then we go across and fill 3p, and then 4s, and then 3d. We hit the 3d block, and then we hit 4p. After 4p comes 5s, then 4d, then 5p, and then 6s, and then it's weird and it goes down here to 4f, and then it comes back up here to 5d and 6p, and then lastly 7s down to 5f, back up here to 6d, and then 7p. So this is the order of filling, and you could write it out just based on using your periodic table and not having to reference that energy diagram and see the different energy levels. All right, so we're going to write electronic configurations for the following using our periodic table. So rather than counting electrons, we can just read across the periodic table. So I'm going to erase this mess and show you with these examples. So the first one we have is aluminum. And you can't tell here, but aluminum, if you look at your periodic table, is, I want to make sure I get it right. So aluminum is right here on the periodic table, okay? So we're going to start here, and we're going to fill up to that point. So we have a full 1s, so we've got 1s2, and now 2s2, and now 2p6, and 3s2, and then we're at aluminum right there is the first P. So that's 3p1. And that would be aluminum's electronic configuration. All right, now the next one is titanium. And titanium, I'll erase this. Titanium is right here on the periodic table. So we're going to do the same exercise, and we're just going to fill up until we get to titanium. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we go in 2 places in the 3D. So we're just going to write that out. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, 2 places in, 2 electrons. All right, and then this last one, lead, is a tricky one. I might challenge you to pause the video and try it yourself. I'm just going to write it out here, and you can check. All right, so lead is pretty far down the periodic table. And we have to go through a lot of energy levels and sublevels and fill up there's a lot of electrons there. How many does lead have? Where is the periodic table? Lead is number 82. That's 82 electrons that we're filling out there, okay? So we said that electronic configuration is a shorthand configuration for orbital diagrams. But as we can see with lead here, sometimes electronic configurations can get out of hand and really long. And so we have a shorthand for the shorthand. So shorthand electronic configuration, we also call it noble gas shorthand or noble gas configuration. Because we use the noble gases as a way to abbreviate. All right, so we use the previous noble gas as a way to abbreviate the first set of electrons, and then we only specify the outermost electrons. So for aluminum, titanium, and lead, which we just did up here, all right, I'll show you the electronic configuration. So, or the noble gas configuration. So aluminum, if we look at the periodic table, all right, the noble gas before it is neon. So we can write neon in brackets. And the noble gas, or the electron configuration of neon, is this right here. All right, so basically we just abbreviated all of that as neon, and then we just have to write the leftovers, 3s2 and 3p1. So that certainly simplifies it. Titanium, all right, the noble gas before titanium is argon. And the electron configuration for argon is going to end in 3p6 because it's in the third row, at the end of the third row of the periodic table. So it will be 3p6. So we just abbreviate all of that as argon, and then we write 4s2, 3d2. So that really helps simplify it, and it's especially obvious for lead. The noble gas before lead is xenon. Xenon is 5 rows down, so it's going to end in 5p6. So I'm going to outline all of this up to 5p6. Okay, all of that is xenon's electron configuration. So I just shorthanded all of that just by writing xenon in parentheses. And then the rest, the leftovers, are the 6s2, the 4f14, 5d10, and the 6p2. All right, so I have a couple here for you to try. You might want to pause it and then restart it and check your answers. So I'm just going to write them here. Okay, so using your periodic table, you should be able to do that pretty quickly, not having to write out all of these different electrons and count up to the number of electrons. So using the periodic table makes electron configurations much quicker, much easier to write out and to view. And this noble gas configuration is not just convenient and easier to look at and write, it's actually highlighting the most important electrons in an atom, which are those outermost electrons. So the outermost electrons are called the valence electrons. This is an important term that you will hear a lot this semester. Valence electrons are like the key to chemistry. They are why atoms behave the way they do, why chemical reactions occur, both in inorganic and organic chemistry. It's all about these outermost electrons. They're the ones that are most likely to leave the atom and go do other things, get themselves in trouble. So valence electrons are super important. So what are valence electrons? They're the outermost electrons. And for main group elements, the outermost electrons are the ones that are in the outermost energy level. Okay, so any of the ones that have the ones that have the highest N number. Lena, you can leave the dog alone. You're making it louder.
Sorry.
Thanks, though, for trying to get him out of here. Okay, so the main group elements, it's super easy. Whichever ones are in the outermost N level that have the highest N number are going to be the valence electrons. For transition elements, it's a little tricky. So it's any that are in the outermost energy level and any that are in any unfilled D sublevels, right? So those are how you find valence electrons. Anything that's not a valence electron is a core electron. And those include all the previous noble gases, gas electrons, so the stuff that we don't even write because we're indicating it as a noble gas, and any filled D or F sublevels. Okay, so for example, we've got 3 examples here. Silicon. Silicon's a main group element. Okay, you can find it in, it ends in P2, so you can find it in 2 into the p block. Okay, so for main group elements, anything in the highest energy level. The highest energy level here is energy level 3. So all of the energy level 3 electrons are valence electrons. There's 2 in the s and 2 in the p. So that means there's a total of 4 valence electrons here. And the rest of them, 2 plus 2 plus 6, the rest are core electrons. So there's 10 core electrons and 4 valence electrons, which should add up to 14, which is silicon's number on the periodic table. Arsenic, all right? Arsenic is also a main group element. And so for main group elements, we only count the ones in the outermost energy level, okay? The outermost energy level, right? Any electrons in filled D or F sublevels, like these, are part of the core, all right? So these 4s2 and the 4p3 are our valence electrons. So that's 2 plus 3 is 5 valence electrons. And all of the rest of them are core. I could add them up, but what I'm going to do is look at arsenic, and I see that it is element 33. So 33 minus 5 means that the rest of them, the other 28 electrons, are in the core. And then manganese, now if you look at the periodic table, manganese, Mn, element 25, is a transition metal. And for transition metals, it's any in the outermost energy level, so that 4s definitely is a valence electron, but also any electrons in unfilled d orbitals. So that d orbital there is not full, so these are, all 7 of these would be valence electrons. And the other 2, 4, 6, plus 12, 18 electrons are core electrons. Okay? So, fun fact though for you, with these main group elements, you can figure out the valence electrons. You don't even have to write out the electron configuration. You can cheat and just determine it from your periodic table, because as it turns out, for the main group elements, the group number tells you how many valence electrons they have. Watch this. Where's silicon? Silicon's right here. It's in group 4, and it has 4 valence electrons. Arsenic, where is it? It's in group 5. It has 5 valence electrons. All right, so all of these guys in group 1 have 1 valence electrons. These all have 2 valence electrons. And then we skip over to the main group over here. 3 valence electrons, 4, 5, 6. Boom, right there. You don't even have to do any electron configuration to figure it out. You just look at the group number, and that will tell you how many valence electrons there are. And like I said, valence electrons are the most important ones for chemistry. They determine the chemistry that happens, and they determine chemical bonding. So they're the ones we care about the most. So having a really quick and easy way to determine them just by looking at the group number on the periodic table is super convenient. So, pop quiz, quick question for you here. How many valence electrons do each of the following atoms have? Pause the video, search yourself, write them down, and check your answers. This is also going to be good practice for just learning your way around the periodic table. All right, so hopefully you found all of those, and the number of valence electrons is equivalent to their group number, the column number. So I keep calling it the group number. That's because with the periodic table, the columns, we call them groups or families, but more commonly they're called groups. All right, so this is a little anatomy, basic stuff about the periodic table. Now that we already know that it's all arranged based on electrons and their configurations, now I'll just talk about some general stuff. All right, so the columns are called groups. The rows are called periods. And the rows are numbered 1 through 7. So 1, 2, 3, 4, 5, 6, 7. And the groups or columns, there's 2 different naming systems. So the old one is the A and B. So where the main group elements are 1 through 8A, and then the transition elements are 1 through 10B. I like that naming system because that's what I learned and grew up with, so that's what I stick with. But that's actually the old school way. The new way is to just number them straight 1 through 18. And I think different textbooks will stress different ones too. A lot of times they'll name both. They'll call, column 1A 1 or 1, And this periodic table that I've pasted here is color-coded for your convenience to identify the 3 different types of elements. The most abundant type of element are metals. And metals are pictured here in yellow. They're all on the left side of the table. They are good conductors of electricity. They are shiny and usually solid at room temperature. They are very flexible, so they're both malleable and ductile. Malleable means that they can be pounded into flat sheets that are flexible, and ductile means they can be drawn into wires that are flexible. All right. While metals are the most abundant type of element on the periodic table, they're actually the minority of elements on planet Earth. Most of the mass, if you calculate the mass of elements on Earth, it's mostly nonmetals. So that's why there's a lot of precious metals, because there's a lot of metals that are only in very small abundance found on Earth. All right, so sort of the opposite of the metals are the nonmetals. And they are colored in blue, and they're on the right side of the periodic table, with the exception of hydrogen, which some might argue would be better on the right side of the table, but it only has 1 valence electron, so it fits in column 1. But it's sort of an oddball there. Nonmetals are poor conductors of electricity and heat, but that does make them good insulators, so that has value. Solids are not flexible and malleable and ductile. They are, nonmetals, their solids are not flexible. They tend to be very brittle, and they tend to have a dull appearance, so not shiny, more like powdery or matte colored. And they represent all 3 states of matter. So if you look at the font in this diagram here, anything in black is a solid at room temperature. So most of the metals are solid, with mercury being the one exception, being a liquid at room temperature. But if you look at the nonmetals, the ones in blue font are gases at room temperature, and then bromine is a liquid at room temperature, and then some of these other carbon, phosphorus, sulfur, iodine are all solids at room temperature. So they span all 3 states of matter. And then in between the metals and nonmetals, you have the sort of the border patrol there. And those bordering elements, they kind of act like metals and they kind of act like nonmetals. We call them metalloids. And the metalloids have some properties of both metals and nonmetals. One thing about them that makes them special is that they are really good for use in semiconductors, because they can conduct electricity like metals do, but they have the ability to form materials that conduct electricity only in one direction, which is really important for electronics, which is why like the electronics capital of America in California is called Silicon Valley. Silicon is a metalloid that's used a lot in semiconductors for electronics. So, still sticking with some general anatomy of the periodic table, some of the groups have names, special names, and there are 4 groups that we use those names a lot, so you need to know them. So group 1A are called the alkali metals. And the alkali metals all have 1 valence electron. They're very reactive elements. They react really violently with water a lot of times. Not hydrogen, but all the others are very reactive. So, no, hydrogen is very flammable. But like Sodium is group 1. You put sodium in water and it like basically explodes. It reacts very violently. Group 2A are the alkaline earth metals. And they all have 2 valence electrons, and they're also pretty reactive. All right. Then we skip across to group 7A. The other groups, like 3, 4, and 5, do have names, but they're not as, we don't use those names as often. So the group 7A elements are the halogens. And the halogens, of course, all have 7 valence electrons. And they have this trait of reacting really easily with metals. That's what one of their chemical properties. That is why they are grouped together. And then 8A are called the noble gases. And the noble gases have 8 valence electrons. And turns out that 8 valence electrons for main group elements, for all main group elements, 8 valence electrons is the amount that fills the outer energy level. So for any energy level, all of the S and P orbitals are filled. And it turns out that that's a very stable state. And that results in these noble gases being very non-reactive. Or we say inert, means non-reactive. And it's because of the fact that their valence shell is full that makes them very stable. So they don't do reactions. And the reason they're called noble gases is because early chemists recognized this inert property, this reluctance of the noble gases to react with other elements, and kind of compared them to nobility, the snobby upper class who won't consort with people of the lower class. They only hang out with themselves, and they won't, dirty their reputations. I don't know why I'm putting on this voice. So the noble gases, I like to think of the noble gases as being complete. Their outer shell is totally full. Their valence shell, their outermost shell is totally full, and they are complete. They are not lacking for anything. They are satisfied in their life, and they're happy. And so they're good with what they've got. Whereas basically all the other elements on the table are not very happy with their state of life. They ultimately want to be complete and full and stable like the noble gases. So if you look at the other end of the periodic table in group 1, you have those highly reactive group 1 elements, all right? That's because they have this one lonely electron in their valence shell. And that valence electron, they'd really like to have a full valence shell. And until they have a full valence shell, they're really unstable. It makes them really unstable and reactive, and they will do whatever they need to do in order to get a full valence shell and be happy and stable like the noble gases. So, like we said, for pretty much all elements, for all of these noble gases, their valence shell is full with 8 electrons. And so basically all atoms are trying to get a full valence shell with 8 electrons. And so a lot of chemistry is governed by this rule that we call the octet rule. This idea that elements really want a noble gas electron configuration. They'll do anything, and they'll do reactions and create bonds in order to fill their valence shell. All right. And one way they can do this is by gaining or losing electrons. And when that happens, they go from being neutral atoms to being charged particles that we call ions. So an atom is neutral, an ion is charged. And again, they do that because they want to have the same electron configuration as the noble gases. They want to have a full valence shell. So we say that they want to be isoelectronic. Isoelectronic with noble gases. That word literally means same electron structure. Okay? So ions can be positively charged. We call those cations. Or they can be negatively charged, and we call those anions. So the mnemonic for that is cats have paws. So cations are positively charged. Boom, boom, okay? So cations form when an atom loses electrons. They're due to a loss of electrons. Since electrons are negative, when you lose them, you become more positive. So an example of this is magnesium. Magnesium has 2 valence electrons in the 3s sublevel, and if it loses them, then it ends up with a 2+ charge, and the electrons that are left are the same electron configuration as neon. So a magnesium ion with a 2+ charge has the same electron configuration as neon, and it's actually very stable. So metals, which are on the left side of the periodic table and have 1, 2, or 3 valence electrons, it's easier for them to lose those electrons to have a full valence shell than it is to gain electrons. So group 1A only needs to lose 1 electron, and that'll leave it with a 1+ charge. Group 2 has 2 valence electrons, so it'll lose those 2, and then they'll end up with a 2+ charge. And group 3 has 3 valence electrons. It'll lose those and end up with a 3+ charge. Transition metals are funky. They vary. So they can lose different numbers of electrons in a less predictable way. So for example, copper can lose 1 electron and form a copper+ ion, or it can lose 2 electrons and have a 2+ charge. So copper is a little bit more complicated, and you can't predict it in an easy way like we're going to see with these 3 groups that you can. Anions are negatively charged ions, and they are due to a gain of electrons. Because electrons are negatively charged, you gain them, you become more negative. All right? So nonmetals have a tendency to do this. Oxygen's electron configuration is that it has 6 valence electrons, so it only needs 2 more to fill that shell. So if it gains 2 electrons, now it has this configuration, which is equal and isoelectronic to neon's configuration. But because of those 2 extra electrons, it now has a 2- charge. And since nonmetals are close to being full, they have 5, 6, or 7 valence electrons, it's easier for them to gain electrons and become anions than it is to lose electrons. So in group 5A, they're really close. They need to gain 3 electrons, and then they will have a 3- charge. Group 6A need 2 more electrons to reach 8, and so they'll have a 2- charge. And then group 7A just need 1 more electron to fill their shell, and they end up with a 1- charge. Okay, so just using the periodic table for these main group elements, we can determine the charge of an ion. So I'll do these. Again, you might want to pause your video, try it yourself, and then check back. Aluminum is in group 3A, so it's going to lose 3 and have a +3 charge. Barium is group 2A. It'll lose 2 and have a 2+ charge. Fluorine is group 7A, so it has 7. If it gets 1 more, it will have a 1- charge. Sulfur is group 6A. It just needs 2 more, so it'll gain 2 and have a 2- charge. Nitrogen is 5A, so it will gain 3 more electrons, end up with a 3- charge. And potassium is group 1, so it will lose that 1 and end up with a 1+ charge. Okay, so this will be a skill you want to practice, because knowing the charges that atoms form when they form ions is important for the next chapter when we talk about ionic bonds and ionic compound formation. You need to know what ions these elements will form in order to know what ionic compounds they will form. So good skill to practice. So we've seen that the periodic table is just this masterfully organized chart that has actually so much information we can glean from it, so many things we can cheat using it, like figuring out the electron configuration or the number of valence electrons. And there's some general trends that we see that are important to point out as well. So the periodic trends are atomic size, ionization energy, and electron affinity. So let's start with atomic size. So remember, the size of an atom is not definite and clear because that electron cloud is kind of fuzzy, but also the electron cloud is basically the determinant of the atomic size. Most of the space that an atom takes up is its electron cloud. So since we can't know the exact size of the electron cloud, the closest measurement we can get to atomic size is to measure the distance between nuclei of atoms by measuring the density of their solids. And then we take that distance and we divide it by 2, and we get the atomic radius. All right, so that's how the atomic radius has been measured. So the radius increases as we go down a group, down a column. And that makes sense, and I'm going to show you my little diagram here, because as we go down a column, we're adding energy levels. We're adding levels of electrons. So it makes sense that they will increase in size as the atoms get more and more electrons and more energy levels. As we go across left to right, the radius actually decreases, as you can see in this image. And that is because of something called shielding. Shielding. I probably spelled that wrong. I before E except after C, so flip that. And this is something that core electrons do. They basically block the outer electrons from feeling that positive charge of the nucleus, from experiencing that full charge, or Z, the number of protons. So electron shielding is sort of described as the charge that is felt by any given electron. And the charge that is felt is called the effective nuclear charge. And the equation for the effective nuclear charge is Z, the number of protons, the atomic number, minus the number of core electrons. Okay? So the higher that effective nuclear charge, the more electrons are attracted to the nucleus, and sort of the tighter that the size will be. The tighter it will hold on to those electrons. So as we move from left to right, you can see that the effective nuclear charge goes up. So for sodium, which is a period 3 in the third row, all right, so is chlorine. Scratch that out. That doesn't make sense there. Okay, so the effective nuclear charge for sodium is going to be Z, 11. Sodium is element 11, minus the number of core electrons. These are the core electrons. There's 10 of them. So that has an effective charge of 1, an effective nuclear charge of 1. The valence electron there feels a very small effective nuclear charge. In chlorine, though, chlorine is element 17, so its Z is 17, minus core electrons. It has the same core electrons that sodium does. It's in the same period, so minus 10. And it has an effective nuclear charge of 7. So its valence electrons feel a much stronger pull toward the nucleus. And that's because it has more protons, but still the same number of core electrons. So my analogy is it's kind of like people standing around a campfire. So sodium has a relatively small campfire, and it has, let's say that's 10 core electrons, 10 people surrounding that fire. And so this one guy on the outside, he's not really very warm, is he? He can't really feel the heat from that fire very well because those 10 other people are blocking him from it, and the fire is relatively small. But chlorine has a larger nucleus. It has more protons. So it's kind of like it has a larger fire. And so even though it still has 10 people around that fire, the valence electrons, the people in this outer row here, they can feel the warmth better because the fire is actually bigger and there's still just 10 people crowding around it. So these guys are they're warmer, kind of like the valence electrons in chlorine are more attracted to the nucleus. So chlorine is a smaller atom than sodium, even though it has more protons and more electrons. You would think it would be bigger, but it's not, because the more protons in the nucleus pull the electrons closer. All right, so that's why you get this weird pattern that you wouldn't expect, that atoms actually get smaller as we move across the row, because the more protons in the nucleus actually attract those electrons tighter and tighter. Another thing to consider is not just the atomic nuclei or atomic radii, but also ionic radii, so the radius of ions. So cations, since they lose electrons, they are always smaller than their neutral counterparts, their neutral atoms. So when sodium becomes a cation, it loses electrons. So it makes sense that it would be smaller because electrons are what contribute to the cloud. But also without those electrons, when it loses one electron, now the other electrons feel that positive pull of the nucleus even more. They don't have to share it with that electron that left. Anions are always larger than their neutral counterparts. All right, so chlorine, for example, is maybe this size, but when it becomes an anion, it gains electrons. So of course it's going to get bigger. That electron cloud is going to be bigger. All right, so quick question here for you. Choose the larger atom or ion from each pair. So we've got sulfur and a sulfur anion. Anions are always larger than their counterparts. Calcium and its cation. All right, cations are always smaller. So the atom in this case is going to be the larger one. And then this one is kind of a confusing problem, and I'm just going to erase it. Kind of hard to compare two different ions of two different charges because it's hard to predict. Okay, the last couple of things. So atomic size is predictable across the periodic table. Another thing that's predictable, and atomic size has everything to do with electrons. Really, the periodic table, guys, has everything to do with electrons. And so many of these other properties of atoms have everything to do with electrons. Like, they should be so famous. They're like so important in chemistry. All right, so ionization energy is the energy that's required to remove an electron from an atom. When I explain this, I always do this little plucking motion, like I'm plucking an electron out of an atom, okay? So if you have some atom and you remove an electron, so you take out an electron and what you have left now is a cation, all right? The energy that it takes to do that is called the ionization energy. So to pull one electron out, that's the first ionization energy. Then if you take that cation and you pull another electron out, so now you have a 2+ cation, that's the second ionization energy, and so on and so forth. So you could take an atom and keep successively plucking electrons out, and each of the amount of energy that it takes to pluck each electron is the first, second, third, and so on and so forth, ionization energy. All right, so ionization energy is going to decrease as we go down a group. And that makes sense because the electrons, as we go down a group, we have more and more electrons. They're in larger and larger energy levels that are further from the nucleus, which just makes them easier to remove because there's a whole lot more shielding going on. There's a lot of core electrons that are shielding them from the nuclear charge, so it's fairly easy to pull out an electron. So the ionization energy is pretty low. The ionization energy, however, increases as we go across the periodic table, left to right. And that is, again, kind of related to why atoms are smaller. So the smaller the atom is, the closer it's holding those electrons to its nucleus. And it's doing that because as you go across the periodic table, you have a greater and greater effective nuclear charge. So it becomes harder to remove those electrons. The ionization energy is going to be higher. So real quick question, determine which element in each pair has a higher first ionization energy. So you'll want to reference a periodic table for this. And so on the periodic table, aluminum and sulfur. So aluminum and sulfur are in the same row. Aluminum is to the left and sulfur is to the right. And so we know that ionization energy increases left to right. So sulfur being to the right, all right, is going to have the higher ionization energy. For arsenic and tin, is that SB? No, SB is antimony, I think. They are in the same column. So arsenic is above antimony. And so we know that the ionization energy decreases as we go down. So the one that's higher up has the higher ionization energy. And then with nitrogen and silicon, all right, they are located like this on the periodic table. So here's nitrogen and here is silicon. Okay, so nitrogen is both above and to the right. And silicon is both below and to the left. And both of those things, so if you're above or to the right, that's a high ionization energy. And if you're below or to the left, that's a lower ionization energy. So they meet both of those requirements. So this one, for sure, nitrogen, has a higher ionization energy than silicon. So we can also see trends in these successive ionization energies. So the energy to remove the first, and then the second, and then the third, and then the fourth, and so on and so forth, electron from a single atom. So valence electrons, those in the outermost ring, are going to be easier to remove than the core electrons. So what you end up seeing is when you do successive pulls of electrons, all right, is that you get a really big jump when you go from valence electrons to core electrons. So group 1A, like sodium, has one valence electron. Its first ionization energy, relatively low. But then the second ionization energy, you see this big jump, and then smaller increases in these other ionization energies, okay? That's because that first valence electron was pretty easy to pull, but the second electron was a core electron, so it was much harder. So you get this big sort of leap or jump in energies, okay? So group 1 elements tend to have a very high second ionization energy. You see a big jump there because their one valence electron is gone. The second one is a core electron. Group 2A, like magnesium, has 2 valence electrons. So the first two, the first ionization energy is relatively low. The second ionization energy is a little bit higher, but they're somewhat close together. But then there's this big leap, a big gap between ionization energy 2 and 3. So they have group 2 elements have a really high ionization energy 3. And so you can see this trend continuing. Group 3 elements would have a really high ionization energy 4, a big leap from 3 to 4. Okay, this word here should be core. There are big jumps when you pull out core electrons. All right, so there might be some problems about assessing ionization energies, trying to identify what group an atom is based on its ionization energies. And then lastly, I'm going to just breeze over this, but electron affinity is something that trends across the table. This is sort of the opposite of ionization energy. It is the amount of energy that it takes not to remove an electron, but to add an electron to an atom and make it an anion. And so this can be positive or negative value. And as it turns out with energy, the more negative the value, it's actually the more favorable. So it's kind of weird and backwards, and the reason I'm not getting into it is because the electron affinity actually increases as the energy is more negative, which is very counterintuitive and confusing. So it increases right across a period. In other words, it becomes easier and easier as we go across the period to add an electron to things. Which makes sense because as we go across the periodic table, group 1A, 2A, then I'm skipping over to 3A, 4A, 5A, 6A, 7A, okay? These have more and more valence electrons. So it's easier and easier to add electrons because those 7A, they have 7 valence electrons. They are dying for another electron, and they will take it really, it takes a very small amount of energy to add an electron to those guys. All right. Also, as we go across the table, the effective nuclear charge increases. So they have a higher attraction for these electrons. All right. The sort of caveat and sort of exception here to know is these group 8A elements, the noble gases. Okay. So it increases all the way to 7A, but then the 8A elements have an electron affinity of 0. And that's because they're full. Their valence shell is full. They can't take any more electrons. They cannot form anions. They just can't do it. So their electron affinity, although it increases across the table to the right, the exception is that when it reaches the very far right, those noble gases, it's actually equal to 0. All right, so that is the end. We have reached the end of chapter 3. It was probably a lot if you tried to do it in one go, so hopefully you broke it up into bits. But now you should be experts on electrons, on how to calculate energy of electrons and photons, how to figure out the arrangement of electrons in an atom, what energy levels and sublevels they reside in, how to fill them in the correct order, how to do electron configuration, and some periodic trends and things like size and ionization energy.